So this afternoon's talks, it's Andrew Stuart. He's going to talk about large graph limits learning algorithms. Please. I'll talk. Almost ready.
Thank you, Derek. Is working okay? I'll take that as a yes. I'm an optimist. And this is working okay. Okay, so I'm going to talk about large graph limits of learning algorithms. Specifically, I'm going to talk about semi-supervised learning. And the problem that I'm going to tackle is on this whiteboard, on this blackboard here. So you can refer back to it during the course of the talk. Could we have the lights on for a minute while I just talk about the problem? No, maybe not. Could we have the lights on for a second? Thank you. Let me just say a few words about the general context. There are many problems in machine learning which have exhibited incredible engineering success over the last decade. And as a community of mathematicians, statisticians, I think there are many open problems for us where we can develop mathematical theory to underpin those engineering successes. This is just one small corner of the subject area, and it's a particular small corner which relates to inverse problems. So I want to describe the specific problem that I'll tackle. We can actually tackle more general things than this, but this is a good problem for you to get your teeth into and understand everything that I want to say in this talk. This is the goal of semi-supervised learning in this clean statement. We have two sets of data, what I'll call unlabeled data, and these are points xj in Rd, and there are uppercase N of them. And I'll call these the indices. They belong to the nodes of what will be a graph, Z. And we have labeled data on a subset Z prime of Z. So Z prime is a subset of the nodes Z of size j less than n. These are labeled, and for the purposes of this talk, my labeling will be binary, and so I will label, these labels will just be the numbers plus or minus 1. Being binary is not crucial, and I'll do an example later on, which is many more categories. The goal is to spread the labels to the entire index set J. Okay, so we're given labels on a subset of nodes, but we want to find them on all of the nodes. So I view that as an inverse problem. The inverse problem is to recover the function y, which is in the class of labels, on the entire graph, given limited information about it on a subset of the graph. But lurking behind this is the additional information that on the entire graph we have this unlabeled data. Okay, so that's the mathematical problem, and it's prototypical of many classification problems in machine learning. So the work I'm going to describe is a synthesis of 3 papers with a number of collaborators. The first, with Andrea Bertozzi, Michael Luo, and Kostas Zigoulakis, is a formulation of this problem in a Bayesian setting, which is how I'll start. The second paper with Matt Thorpe, who is here, Diane Slepchev from CMU, Matt Dunlop at CALTECH, is a study of this problem in the limit where n goes to infinity, and so the graph becomes an infinite graph. And in doing that, I'll answer some questions about how you might approach this problem using Gaussian process regression and how to choose the kernels. There's, so to speak, a canonical answer about how to choose kernels in Gaussian process regression by taking this n to infinity limit. And then there's also some work on algorithms with Michael Luo from UCLA, Andrea Bertozzi, and Victor Chen, and Omeros Papaspiliopoulos. Okay, so I'll give some orientation, carrying on from the orientation I've just started to give you. I will give you some background on the graph Laplacian. Most of you, or many of you, will know it, but I don't want to make that assumption. So I will tell you about the graph Laplacian, which is determined entirely by the unlabeled data, but which we will link to the labeled data through a modeling assumption that I will explain to you. I'll formulate this in a Bayesian, the problem on the board in a Bayesian fashion. Take the large graph limit, n goes to infinity, and describe some numerical result. And I welcome questions. But please interrupt if anything is not clear. So this is the problem that I've described on the board. And let me just say a little bit about the history. And this particular problem with binary labeling, you can formulate in a combinatorial way using a formulation of finding the minimum graph cut, where the graph is a graph computed from the unlabeled data using edge weights computed by using the affinities of the two nodes at the end of each edge. That combinatorial problem is soluble in the case of binary classification, but not when you go above two classes. So in 2003, Zhu, who was a PhD student at CMU, together with Garamani and Lafferty, formulated the problem using the idea of harmonic functions, which relates to Gaussian process regression, and which I'll come back to later in the talk. It was a nice paper, nice thesis, but this particular formulation has modeling issues, which I will highlight and describe the differences with what we do later on. The idea of relaxing the combinatorial problem, so the combinatorial problem is to find labels purely in the set plus or minus 1. This was relaxed in a paper of Bertozzi and Flenner using ideas from statistical physics to penalize deviations from plus or minus 1, but allow the labels to live in the real numbers, just close to plus or minus 1. And there's a nice literature review which you can find by Zhu coming out of his PhD thesis, which is easily accessible on Google Scholar. Okay, that's the problem, and the talk has two components. One I've just told you by putting this red stuff up here. It's formulating the problem in a Bayesian fashion. I'm going to use the unlabeled data to create a prior. So this is part of actually something that's more general and ongoing in machine learning and Bayesian methodology in machine learning, which is using data to create priors. So rather than creating priors purely based on mathematical intuition and maybe a couple of moments, to actually build the priors using data. So I'll explain how that works. The label data will be viewed as a likelihood, and I will giving a likelihood, and I will link then this labeled data to the prior, and then we will compute a posterior distribution using Bayes' theorem. So that's a method. So that's one idea that will be in the talk. And then the other idea in the talk is that I will just let n go to infinity and look at what that tells us. I see I have different n's. Hopefully I'll be consistent about that. Okay, any questions about the problem? Okay. So where we're going to get to by taking the limit n goes to infinity is a continuum inverse problem, which will be formulated as finding a function on a bounded open set D in Rd. Rd is where the unlabeled data live. D prime is a subset of D, and the ill-posed inverse problem that will come out of this large graph limit is somewhat like regression, but it's a classification version. We're trying to find a function u from D to R given only the sign of u. Okay, so I'm going to assume we're given the sign of the function on D prime, which is a subset of D. Okay, that's an inverse problem, and it's a hard inverse problem, harder than regression. It's very similar to regression, but we're only observing the sign of the function. Okay, so regression, you would observe the function itself. We can add noise into this, but that's not really the essence of it. If you're going to solve a problem like this, you need a lot of prior information, and the prior information is going to come from the unlabeled data, which is going to induce very strong correlations on the function u that I want to find here. Okay? So I will explain to you how that happens. Okay, so the kind of, just in pictures, the kind of problem we're solving is like this. We're given a function u, we're given the sign of a function u. So the function is positive here, negative here, and we don't know anything about it where I've colored yellow. And we're going to recover a function u whose sign agrees with that data. And here's the recovery of the function. Now obviously there are many functions consistent with this, what I've shown you here. So for me to be able to go to this, I need prior information. And again, to say it again, the prior information will be unlabeled data in a continuum limit. Okay, so to understand this talk, you need to know a couple of things about the graph Laplacian. I'll say them in words and then I'll go through them in formulae. The graph Laplacian is a way of encoding correlation information in data. Here I'll take the data in RD, but using kernel functions the data can be anywhere, provided you have some notion of metric and affinity between the data points at the nodes. So we're going to make a graph with nodes z from 1 to n, and at each node will be a point xj in RD, and then we'll make a weighted adjacency matrix on the edges of the graph. And I'll come to the details of this later, but it'll be a function of the difference between xj and xk. And roughly speaking, this will be measuring the affinity between those points. So the weights will be high if xj and xk are similar, and the weights will be low if xj and xk are dissimilar. Okay, so this is weights which describe the affinity of the points at the end of each graph. And to make the graph Laplacian, you compute the diagonal matrix found by summing this adjacency matrix along rows, and then subtract the adjacency matrix W from D, and we will scale it for the purposes of taking a limit later on. This is the unnormalized graph Laplacian, and there are theorems if you use the normalized one, for those of you that know what that is. So L has some nice spectral properties. The quadratic form ULU in Rn is positive definite, and can be written as these weights are positive, can be written as the weighted sum of uj minus uk squared. If the graph is fully connected, the first eigenvalue is 0 and corresponds to the constant eigenvector, and that's the sense in which it's similar to the Laplacian. And if it's fully connected, then the next eigenvalue is positive, and the eigenvector that goes with it, Q1, is called the Fiedler vector, and I'll show you that in a minute because it's important.
Yeah. The spectral properties for free just by the way you constructed it, or is there something about Ada that makes this all?
No, only that the weights are positive and or non-negative and fully connected. Then you get this for free. That's it. But I will put more structure on Eta later, a lot more. But at this point, nothing more than that. So the way I'm going to connect the unlabeled data and the labeled data is through a Gaussian process. So this is a real valued process that lives on the nodes of the graph. I still yet have to link real numbers with binary classification, and that's yet to come. But first of all, I just want you to appreciate that through the graph Laplacian, I can make a Gaussian process, and I'm going to do it by a covariance which is found by taking the graph Laplacian, shifting it, and raising to the power minus alpha. And I'll say why later on, why that's a good thing to do. But what you should really understand is that this Gaussian process encodes correlations in the unlabeled data. And I'm going to show you that by means of an example. I'm really sorry about the temperature in this room, and if everybody's asleep at the end, that's fine with me. I will try and be awake. But look, we don't even have the windows open. This is like, thank you. There's one, I mean, no, it's bad for the people sitting next to the window, but for everybody else, it's much better if they're open.
It's a small price to pay.
Sorry, guys. Now I know why the window is closed, because you didn't want to sit. I'm with you on that. I mean, you've got to look after yourself in this world. Right? But I'm looking after myself because I want an audience that's awake. So. This is an example of what you can do with the graph Laplacian. This is based on a collection of votes from the US House of Representatives. That's made up of 435 people in 1984. And there were 16 votes. So for each member of US House of Representatives, you have a vector in R16 made up of +1 if you vote yes, -1 no, 0 if you don't vote. Using that, you can compute the graph Laplacian and find the Fiedler vector. And along here are the members of the US House of Representatives, and they're divided by party. Everybody up to here is a Democrat, and everybody up to here is a Republican. What I'd like you to see immediately from this data set is that if I simply threshold it by its sign, I would make a pretty accurate classification as to who was Republican and who was Democrat. I would be wrong only about the people below the line here and the people above the line here. And so what you need to take away from this is that if you form the graph Laplacian and you compute the Fiedler vector, which is the first eigenvector, it has in it already information about the clustering of the data, independent of labels. So you can lift that up to the Gaussian process. So I've taken the same example. Just look at the red here. The red is the two-point correlation of the sign of u. So u is a Gaussian process. I take its sign, that's +1 or -1, and I look at its two-point correlation, say for the red person, with everybody else in terms of how they voted, and then how that's encoded in this Gaussian process. What you see is that this red person, obviously, autocorrelation of 1, and then correlation with most of the Democrats on average, since this person is a Democrat, is much higher than the correlation with most of the Republicans. Not exclusively accurate, because there are some Republicans who voted more like this person than some Democrats. And this is a process. I'm just looking at one statistic from it. So again, what you are to take away from this is that the Gaussian process, which I'm going to use as a prior, has information about correlation in the unlabeled data. So everything in this Gaussian process is about the unlabeled data, and later I'm going to take the limit where there are an infinite number of unlabeled data, and I'll get a Gaussian process which is defined on a continuum. Okay, any questions about graph Laplacian? Yeah.
In this example, aren't the votes the labels? Or
No, they're not. Sorry, it's a bit confusing because the votes are +1, -1, and 0, but they are viewed for the purposes of this example as a vector in RD. The labels are, I should have said this, thank you. The labels are +1 is Democrat, -1 is Republican, with no political judgment intended by the choice of sign. Okay, so let's formulate this in a Bayesian way. So you can keep the example of the voting, you can keep in mind throughout the talk, but we will let n go to infinity, which will not include that example. So just to recap, we have this unlabeled data, which will be the voting records of 435 people. You make a graph Laplacian from it, and then we put a prior, which is a function from the nodes of the graph into R, and it's going to be a Gaussian prior. Since there are n nodes of the graph, equivalently that's just a vector in Rn, and we have a prior on Rn, and that's a Gaussian. And the Gaussian is found from the graph Laplacian, shifted by the identity multiplied by tau squared and raised to the power -alpha. All you need to know, the parameters matter, and we actually learn them hierarchically later, but what you need to know is that this choice of prior will tend to concentrate on the Fiedler vector, and therefore to represent the correlation that's already present in the unlabeled data. Now here comes the key modeling step, which is how we link all of this stuff about the unlabeled data, which lives in the reals, to the labeled data, which is categorical and lives on +1, -1. And we do that by assuming that the labels are found, roughly speaking, up to some small noise, which I'll come to in a moment, by taking the sign of this real valued process. So if you want to think about the voting records example, the concept here is that individuals are characterized by a real valued process, which takes values in R, but the sign of the process determines what political party they are in. That's a modeling assumption. I'm not defending it, I'm just telling you what it is. Okay? And in general, if you're to solve a problem of this type, where you have data in RD and label data which is categorical, you have to make some kind of model which links points in RD to labels. So here the model is, we make a Gaussian process on the unlabeled data using the graph Laplacian, and we take the sign of that Gaussian process to get the labels. And then that we just condition U on this label information, and we assume there's some noise, which here is found by adding small Gaussian fluctuation around U, the Gaussian process on the graph. And then classification is based on the sign of U, and furthermore we can do uncertainty quantification. So motivation for this work was to be able to do in a defensible manner uncertainty quantification for classifications. That, as you know, there are many things that are done with machine learning and make fairly swift classifications. Understanding when those classifications is uncertain is important, and this is an attempt to try and make a rational way of doing uncertainty quantification for classifications. If you put all this together, U given Y has PDF, which is proportional to the exponential of an objective function. And the objective function I'm going to index by n for the dimension and p for probit, and I'll come back to y in a second. So the posterior is e to the minus this thing. So posterior on u given y. And u, remember, is a real valued process, not RD. U lives on the nodes of this graph, it's real valued, and its sign gives us classifications. The objective function that we would like to, if you want to maximize probability or do a map estimator, you would minimize this objective function. So it has the standard form of a regularizer, which is a quadratic form. So this looks like a Tikhonov regularization, and a function which relates the latent variable u that we're trying to find to the data in a way that I'll come to in a second. So this is prior information, comes only from the unlabeled data, and it will force us to align with the Fiedler vector. That's the rough intuition. And the Fiedler vector does a good job of partitioning the data without even using labels. The second term, okay, this is, I'll come back to probit in a second. What do you need to know about this? It's essentially, if gamma is small, which means that the noise in the model is assumed to be small, this function is something which forces uj to agree with the sign of uj to agree with yj. Psi is the cumulative distribution function for a Gaussian with mean 0 and variance gamma squared. And so this, if you like, this psi, if gamma is small, is a smoothed Heaviside step function. And so if yj and uj have the same sign, that Heaviside step function is evaluated roughly at 1, and so the log is 0 and there's no penalty. So that says if u agrees with y in sign, you have no penalty. On the other hand, if u has the opposite sign of y, you're evaluating the Heaviside step function roughly at, to take a value 0, and the log of 0 is minus infinity, and the penalty is high. So this penalizes u if it disagrees in sign with the label, and it has no penalty, roughly, if u agrees in sign with the label. And then that's smoothed out by gamma. So that particular likelihood is called the probit likelihood, and you can read about it in Rasmussen and Williams, which is a classical text on Gaussian process regression, classification, all kinds of Gaussian process tasks. In that book, they work entirely on the labels and then introduce arbitrarily a Gaussian process which enables them to make inference off the labels. But there's no real principled way in which to define that Gaussian process. What I will show you is that by taking the limit n goes to infinity and using a set of unlabeled data, you can define in a principled fashion a Gaussian process prior for this problem. The specific formulation of the problem here, it comes from this paper with Andrea Bertozzi and Michael Luo and Kostas Vigalakis. Right, there are many other likelihoods you could do, but this one is nice and has the property that this objective function has a unique minimizer. It's a convex function. And so there is a single solution to this problem from an optimization perspective.
I'm sorry, small question. Alpha is responsible for roughness of...
Yes, so you're right.
And but then C looks like a precision matrix and not like a covariance matrix. No,
so if you think of L as being like a Laplacian, or minus a Laplacian, this would be, if L were minus the Laplacian, this would give you up to boundary conditions, this would give you a Whittle-Matern prior, in which alpha determines the smoothness, if you subtract the dimension over 2, and tau is the inverse length scale.
It looks like Fourier of Matern.
It is, if you go into spectral, this is Matern, Whittle-Matern, yeah. It's exactly what it is, and that we'll come back to that later.
But then in this sparse matrix, is it strong assumption that you assume that C is sparse?
I'm not assuming C is sparse, so I'm constructing C from the graph Laplacian. Graph Laplacian is computed from the unlabeled data, that's just given, up to the choice of weight function. And then I'm going to take a limit, and we'll explain how that works. That's work of Matt Thorpe. I'm going to take a limit in which this will be a differential operator in the limit, and it will be sparse. So there's details about what makes it sparse in the limit. At the moment, it's not sparse. Any other questions? Yeah.
This may be a rather vague question, but is there a way to interpret this as an empirical based method where you somehow marginalize out the dependence on the correlations in the graph and you somehow view L as the marginal maximum likelihood estimator?
I don't know the answer to that question off the top of my head, so we should take it offline. We actually estimate tau and alpha using empirical Bayes for some of the computations we do in this case, but I don't think that's what you mean, so we can pursue that afterwards. I haven't thought along that line, and I'm not smart enough to be able to do it online. But thanks for the question.
Sure about that.
Okay, so now I'm going to take the limit I've been babbling on about of letting n go to infinity, and this rests on what I consider to be a very important paper by Diane Slepchev and Nicola Garcia Trios from 2016, and I'll explain to you their result, which we rest on very heavily to take large graph limits of our problem. So the limit theorem I describe here, and the ideas behind the proof I will sketch. There's lots of technical stuff here, but the long and short of it is that, and this comes back to what I was just discussing with Alexander, is that the quadratic form defined by the graph Laplacian, scaled by 1 over n, converges, in a sense which I'll make precise in the statement of the theorem, to a quadratic form defined by a differential operator. That differential operator is a divergence form elliptic operator in which a function rho appears, and rho is the sampling density, and the assumption is that the unlabeled data, xj, is sampled IID from a measure with density rho. And the theorem requires rho to be smooth, to be bounded away from 0 uniformly on D, and to be finite uniformly on D, there to be an upper bound, which follows from the smoothness in any case. So in hand-waving terms, this tells us that the graph Laplacian behaves like a differential operator. The inner product on the right here is L2 with respect to the density rho, and L is self-adjoint with respect to that inner product, and you'll see that in a calculation I describe in the next 2 slides from now. The sense in which they prove convergence, and here is, I think, a really important idea that will be useful in many other contexts, is they use gamma convergence, but in doing so, they introduce a new metric, which is called TL2, and in fact there's TLP. This is a form of Wasserstein distance, but what's novel about it is that, let me make an observation, this inner product on Rn, weighted by 1 over n, can be written as an inner product on L2 rho n, where rho n is the empirical density found by sampling from the measure with density rho. So in doing that, I rewrite this quadratic form on Rn as a quadratic form on function space, functions on the bounded open set D, which is a subset of Rd, but with respect to an empirical measure, so a sum of Diracs. And the convergence result is really about the convergence of this quadratic form to that one. And so in this gamma convergence, they talk about not only the convergence of the functions which attain the infimum, but also simultaneously the convergence of rho n to rho. And that's what the TL metric does. So it's a very useful way of dealing with heterogeneous distribution of points. As these xj's here are randomly distributed, it's a way of dealing with that heterogeneity. So let me make a link with PDEs and Laplacian standard finite difference. So as we discussed earlier, and Derek was asking about, in the generality I've given you here, the quadratic form U in a product LU can be written in this Dirichlet form way, in which you see that it's positive, involves the squares of uj minus uk, and these weights are positive. So the standard discretization of the standard Laplacian in 2 dimensions, we use a 4-point stencil. So the point at the center is just connected to its 4 nearest neighbors. In the generality I'm talking here, on this unstructured graph, every point is connected to every other point. So the orange point is connected to all the other of these xj's. However, and now we get to the details about how these weights are chosen. If the weights are chosen to localize and to put emphasis on nearest neighbors, which is how they will be chosen, then you can do that in such a fashion that any given node is most of its connection is with points near to it. So the scaling that I'm about to describe, which relates to how you choose these weights as a function of n, is one which localizes and enables the intuition you have from, say, Laplacian on a 5-point stencil to carry over to this graph Laplacian on a completely connected graph. Okay, so let me give you the intuition behind the proof. The proof is not done in the way that the intuition that I'm about to give you is given. The intuition I'm about to give you is something that you can find in computer science papers labeled as a theorem, which is not, but it does explain to you the 2 basic ideas that are used in the theorem in the work of Nicholas and Diane. So again, to recap, we have these points xj, which are IID from density rho, bounded open on Rd, and we're now going to choose the weights, wjk, to be a function eta epsilon of the difference between xj and xk. And that, all you need to know is that eta epsilon is like a smoothed delta function. So if xj is close to xk, this will be approximately 1, and if xj is far from xk, this will be approximately 0. So the specific scaling of eta epsilon, the volumetric scaling here, and the scaling of the argument by 1 over epsilon is exactly the scaling that you need for this to behave like a Dirac mass in the limit epsilon goes to 0. Okay, so we just plug this into the quadratic form on Rn, and then the Dirichlet form that I wrote here with that specific choice of weights looks like this. So it's scaled by 1 over n squared, 1 over epsilon squared. All the points that are connected on the graph. This eta epsilon, which looks like a Dirac, and then the difference of u at xj and u at xk squared. So if you just hand waving, let n go to infinity first and use the law of large numbers, this sum becomes a double integral where the xj's are distributed according to density rho of x, the u of x's. The argument x has density rho of x, y rho of y, and eta epsilon is evaluated at x minus y. Okay, so now we've gone to a continuum, and there are limit theorems that will get non-local operators, coming back to Alex's question, out of this. But we're going to take another limit, epsilon to 0. This will look like a Dirac delta function. That will reduce this double integral to a single integral. And you can see ux minus uy divided by epsilon squared looks like the gradient. Okay, so what you get out of this is the gradient of u squared multiplied by rho squared, because we go on to the diagonal of this double integral, and it becomes a single integral. And that quadratic form is exactly the quadratic form that I wrote earlier, the inner product of u with lu in L2 rho. Okay, so there are two things going on. There's a law of large numbers, and there's an approximation of a Dirac by something smooth. In this hand-waving argument, which is not correct, I've let n go to infinity and then epsilon to 0. In the theorem, you have to carefully choose the relationship between n and epsilon and let them go to infinity and 0 together. And that gives information about how to scale these graphs to get this limit. So, and just to show you, if you didn't like all of that, the last three slides, you don't need to remember any of it. I want to go back to what you do need to know. I started with a graph Laplacian, and I've shown you that it behaves like this differential operator. And this differential operator is elliptic, but it's inhomogeneous because it depends on rho, which is the density that I assumed the xj's were sampled from. So, any questions on this?
I'm a little confused. You started without that assumption.
I did.
Now you're going to put that assumption on?
I'm now putting that
relate
assumption
to your
on.
prior or not?
Yes, so it does. So up until this point, I had not made that assumption. It was not needed. When I start the large graph limit, I'm going to let n go to infinity, so I have to say something about where these points come from. And at that point, I make the assumption that they're IID from the measure with density rho, which has the assumptions I've described. So from now onwards,
I'm used to learning where you don't put you have distribution-free learning. You don't put
yes. So
you don't know the prior. You
the
still go ahead and
you can still implement this algorithm without knowing what rho is. But there are implications about how you scale the weights so that you would get a continuum limit if this assumption were valid. And just quick, yes, relevant to what you're saying, there are also theorems of Diane and others where these are, rather than this assumption, you can get a Laplace-Beltrami so that the data is concentrating on a manifold rather than supported everywhere.
I just want to be clear about this rho, which then appears crucially in this result from the limit,
Yeah.
in this continuous, in this divergence from elliptic operator. This rho is somehow inserted a priori by stipulating that the xj are rho IID.
Yeah, I think we're both asking similar questions, really. If you're given data, you don't know what rho is. Nonetheless, you can create the graph Laplacian, and you can carry out the Bayesian inference procedure I described.
Absolutely.
Then you can ask yourself the question, if the data did come IID from some density, and there's a lot of it, what is the Bayesian inverse problem that I've solved? And I'm going to answer that question.
Can you be more specific then about conditions on this density? What do you assume?
Yeah, so for those theorems, there are two theorems. For the one I described, rho is smooth, so just C infinity, and bounded away from 0 uniformly on bounded open set D, and D has nice Lipschitz boundary.
Oh, so it cannot be, so rho cannot be 0 on the boundary of D.
Yes, however, there are other theorems where rho is sampled entirely from a manifold which has 0 Lebesgue measure inside D, and then rather than the operator which I've written here, you get Laplace-Beltrami restricted to the manifold. I'm not touching that case, but that case is covered by the theory of Diane.
Do those theorems or those
There are theorems in that case.
do they say something about the Bayes set, the boundary of the Bayes set?
I don't know the answer to that. Matt thought may know. We can maybe discuss that afterwards. Okay, so you can now, and this is very much Matt Thorpe's work, take what I've described about the convergence of the graph Laplacian and apply it to the quadratic form defined through the graph Laplacian, which you remember was the graph Laplacian shifted by the identity raised to the power minus alpha. And if you carry out an analysis based on the use of this TL2 metric, you can prove that the objective function that we have for the probit method converges to a continuum limit, which I'm now going to describe to you, and point out how it relates to Tikhonov regularization and how it differs from Tikhonov regularization. So the form of the limit has two terms. The second term is the data fidelity term, and it forces the sign, sign of u, to agree with the label y, and the label y is a function which takes values +1 or -1 on a subset d prime of the domain D, from which the points xj are where the points xj live. So this is a data fidelity term, and on its own it would just tell you that the sign of u agrees with y on the subdomain D prime. Okay, so minimizing that that's not a good minimization problem. Infimizing sequences there would be uncountably many ways of doing infimization, and that you could have limits not being attained and so forth. So this needs to be regularized, and this is a form of Tikhonov regularization because C inverse looks like, now we go to the limit, this looks like a Laplacian, although it depends on rho, so it's a divergence form elliptic operator shifted by the identity, c to the -1 is then raised to the power alpha. So this looks like a possibly fractional power of a non-uniform Laplacian, and therefore this looks like a Tikhonov regularization in a Sobolev space. And the Sobolev space, if you think about it, is H alpha. So this is like an H alpha squared penalty, and indeed Diane has proven that the space defined through these fractional powers of operators embed continuously into the regular Sobolev spaces. So this looks like a Tikhonov regularization, but it has a difference from standard Tikhonov regularization, which is that the operator L, which appears in C inverse, is not just the Laplacian, which is what you would get in standard Tikhonov regularization, but this weighted Laplacian or divergence form elliptic operator in which the sampling density rho appears. So this theorem gives you a canonical way of defining regularization for this classification problem in the continuum limit, and as I promised earlier, it gives you a way of answering the question that's unanswered in Rasmussen and Williams, which is how should you choose your Gaussian process regularization. This is a canonical way of doing so. If you formulate the problem through a graph Laplacian, take the large data limit, then this is a natural regularizer, Tikhonov form, but it has information about the structure of the data in the regularizer, whereas standard Tikhonov regularization would only tell you about smoothness. There's no information about the solution to the problem other than smoothness. This has information about the solution to the problem, and in particular in this binary case, it forces the solution to want to live near the Fiedler vector. Okay, so it looks like this limit looks like an inverse problem, it looks like Tikhonov regularization, and it has an additional feature, which is that there is data, information from the unlabeled data that appears in the Tikhonov regularizer.
Are there any specific conditions on the sets?
Yes,
Any plus and D minus?
they have to be separated. You need a separation between them.
They could be rather irregular. Is that correct? I mean, could they be fractal?
Actually, that's a good
Could they
question.
be multiply connected?
They can be multiply connected. Off the top of my head, can't answer the question as to whether they can be fractal. I don't think our analysis allows them to be, but I don't know how sharp we are with that. We should discuss that with Matt afterwards. But certainly multiply connected is fine. Okay, we don't have a limit theorem for the Bayesian version of this problem, but I should point out the work of, again, Nicola Garcia Trios and Daniel Sansalonzo, who have studied other Bayesian inverse problems coming out of this formulation, not probit, in which they have generalized this notion of TL2 convergence to deal with probability measures, and they do have limit theorems for Bayesian inverse problems, and I'm confident that will apply to what I'm going to describe here. But what I'm going to do is simply write down a Bayesian inverse problem that corresponds to this map estimator, and then study what happens to it when the noise in the observations goes to 0. And I'm going to do that because in doing so I can make a link to the original work of Zhu, Garamani and Lafferty and explain to you why this is a better model, which is a modeling statement, not a mathematical statement. So if alpha, and this is the reason why we keep alpha, is bigger than d over 2, then the limiting Gaussian process associated with this Dirichlet form is well defined on L2 rho, and that's an if and only if statement. So if and only if alpha is bigger than d over 2 is the Gaussian process associated with the Cameron-Martin norm defined by this quadratic form. If and only if alpha is bigger than d over 2 is that a well-defined Gaussian process. So, and if it is, alpha is bigger than d over 2, we call that Gaussian process P. Then our posterior is just proportional to e to the minus this probit thing times that Gaussian process. And this is the large graph limit of the prior to posterior map, or the Bayesian inverse problem. Now, if you take gamma to 0, so what is gamma? Gamma, I assumed that the label was found by taking the sign of the latent process, which is the main target of inference, with the addition of Gaussian noise. And the Gaussian noise is assumed to be variance gamma and centered at 0. And I'm now going to let gamma go to 0. So if you let gamma go to 0, then there's a simple weak convergence argument that shows that this posterior distribution converges to what I would say is a canonical probability problem that characterizes the classification problem. And that's this, that you become interested in the non-Gaussian measure on u given y, which is found from the Gaussian prior, which contains information about the sampling distribution, conditioned to lie in the set A. And the set A is the set where the sign of u agrees with the labeling information. So just to recap, P is Gaussian, but the posterior is not Gaussian. It's Gaussian conditioned on this sign information. Now, so what did Zhu, Garamani and Lafferty do? They didn't take the continuum limit. They worked on the graph, but they worked with harmonic functions, which essentially means they were doing Grace-Waber stuff. So they're looking at Gaussian process regression restricted to a graph, and they were finding harmonic functions. So harmonic functions are the map estimators associated with exactly this measure where the sign is removed. So they were solving the problem where you condition the Gaussian so that the latent variable u is equal to the labels. So that was nice and is a reasonable method, but it's a bit weird because it makes a connection between a real valued variable and classification. And it's totally arbitrary. I've labeled these classifications +1, -1, or you can label them as +10, -10. And you would get a different problem if you labeled them that way. So from a modeling point of view, it's not very sensible to connect the real valued latent variable with classification data directly, whereas the sign function is a defensible model. So this is preferable, I believe, from a modeling point of view. Of course, one of the reasons of the success of this harmonic approach is that everything is Gaussian, so it's closed form, whereas this involves sampling. So I just want to finish by showing you that where the original example that I gave at the beginning came from, by just showing you the output of sampling that posterior distribution using MCMC. So on the bottom is where we're sampling. So this is the latent variable. And you see, okay, I haven't told you what the data is, but you can kind of guess. The data is concentrated on these two manifolds here. And what you're seeing is that the latent variable is concentrating spending a lot of time near the Fiedler vector. The Fiedler vector is concentrating on these two arcs. It takes opposite sign on those two arcs, and is the data is labeling one of the arcs as +1 and part of it as +1 and part as -1. The sign of U is what you see up here. So the key point you can understand from this is that the labeling is quite uncertain in this problem. So the label interface is where you change from red to blue, and that interface is moving around a lot. So from this you can compute posterior classifications, and you can get some idea about where the classifications are good, and that means they have low variance, and where they're bad, which means they have high variance. So just to recap, the two ideas in the talk were, one, it's a good idea, as I think I've just shown you, to formulate classification in a manner which enables us to do uncertainty quantification. That will guard against poor classification. And taking the large graph limit gives insight into how these algorithms work and how you might choose Gaussian process priors in the general case. Thank you. Thanks.
So I have a naive question, and it was that you said you were weighting based on the closeness of the two objects. So in the case of politicians, how do you define closeness? Like whether or not their seats are next to each other? Right?
No. Sorry, I know it's there's lots of information in the talk. The closeness was based on how they voted.
Okay, got it.
So if they had an identical voting record, then that would be maximally close. If they differed on one vote, then that would show up. And if they voted completely opposite, then that would show up as that being anti-correlated. Thanks.
So maybe I can ask my question sort of in a more precise fashion now. So once you have made this insight about this limit of the graph, you get this density rho and let's say this nice, then I could in principle put a prior on rho and sort of work through exactly your model, and and I could either be fully Bayesian by dealing with the prior on rho and not using the graph Laplacian, or what one would sometimes call empirical Bayes is that one somehow maybe tries to see the dependence of a sufficient statistic that pops up in the likelihood on rho and sort of just maximizes over that. It would be quite conceivable that putting the empirical graph Laplacian there is some sort of formal empirical Bayes procedure like
I see
that.
what you mean.
And
that's a really good idea. I completely agree with you.
So my question is, in a way, obviously from a computational point of view, it's probably more attractive to actually put the graph Laplacian in there. But from a principal point of view, because you always emphasize that this is canonical, one could just put a prior on rho, and then you would maybe not have to choose your alpha and your tau and so on. And I'm just curious if this is something that you think one could investigate, or whether this.
Yes. I wouldn't. I would say you might want to learn tau and alpha as well, because they're independent of the choice of rows. I mean, in this scaling limit, rho appears, but tau and alpha show up in the limiting Laplacian, non-limiting elliptic operator. But what you suggest is very interesting. You could indeed be hierarchical about rho as well as tau and alpha. So we have done computations where we're hierarchical about tau and alpha, but not about rho. But especially for the reasons behind Ron's question and Christoph's question, we don't really know rho, so being hierarchical would be good. Thanks.
So in classical, like, there was a point in history where people no longer did probit, they switched the logistic.
Yeah.
Operator. I mean, is there some reason you stuck with the the traditional probit in your thresholding in your calculus?
We can do other things. Depends which theorem you're talking about. If you have insight into why people preferred logistic over probit, I'd be happy to hear it. That would be helpful to me. I just stuck with probit for the most part because it was adapted mostly to simple exposition of a number of other things which weren't in this talk. So for example, the level set method which can be used to solve this problem is identical, except you commute the order in which you add the noise and take the sign. If you take the sign and then add noise, you get a slightly different inverse problem. But actually it has the same weak limit as the one I described here. So I think that the thing I wrote down with the Gaussian measure conditioned on the sign of the process, that's kind of a canonical thing which should be independent of logistic probit, level set or whatever.
Is the choice of the Laplacian, like you use the graph Laplacian first to, and then you compute that like an adjusted graph Laplacian with the tau square I added to that.
Yeah.
But instead of the Laplacian matrix, if I just replace it with some kind of a distance matrix between those xj's, will there be any change in the method, or will it affect the results that you?
Yeah, I mean, I would, in terms of the theory, we've really developed it specifically for the graph Laplacian. I have done separately with that voting records calculation, just computed empirically the correlation in the data and used that rather than graph Laplacian. When I did it, that didn't work as well, but that doesn't mean anything. If you know anything about my programming, the content of that statement is 0. But I think the general answer to your question is that the graph Laplacian has emerged as a canonical way of encoding correlation data, but there are others. And also, a question one might ask is, I've taken a limit in which the graph Laplacian becomes a differential operator, which is local, as we've discussed, and that has computational advantages. That doesn't mean it's the best thing to do, and there are also limit theorems for graph Laplacian where it becomes a non-local integral operator, in the paper of von Lutzberg, for example. And answering the question, which is the better limiting process, is also an interesting one. I don't know how to do that.
This is a more philosophical question I'm trying to understand. You began with your problem, and it seems reasonable to assume you don't know rho. You don't
Yes.
know u.
Yes.
But then, to get a theorem, so you can pick any method to do this, right? I mean, there are zillion
There's lots of methods.
methods to do this. And then the question only is, what are the theorems? That is, for which rho, which u, does your method perform well? And your model classes are connected with your method, right?
Yes.
They're very much connected with your method. So how do I, as a guy that knows nothing, compare all these different methods and say I should use Andrew Stewart's
So
graph Laplacian rather than random forest or whatever you're using?
Yeah. I'm not advocating that this is the final answer to what one should do. I'm simply saying there's theory behind this which might be the basis of answering that question. With a couple of collaborators in CALTECH, we're studying posterior consistency results for this method, which give error estimates on the classification as a function of the data size, on the assumption that the data is generated in this way. Those kind of results, which quantify error and could be combined with cost of algorithms, are the ones which eventually might enable a satisfactory answer to your question in large data limits by looking at the cost accuracy trade-off for different algorithms. But we're very far from that. At the moment, I would only defend what I've done in saying that it gives insight, which I believe is helpful to understand that problem.
So there is usually in these methods there's a big breakdown as d gets large. D,
Yeah.
little d.
So you can.
Do you have a big breakdown when little d gets large?
Yes, there's a big breakdown because the methods that I used, so that I did that sampling was d equals 2. So the methods I'm doing are based on differential operator diagonalization, Cahoon and Loewe, and that will be very expensive in high dimension. So in D high, you would need to think about how to do some sparse Cahoon and Löwe.
Okay, why don't we thank Andrew for a great talk?
Thank you.